Hi everyone, how's it going? This is Siri and I'm back with another PyTorch video, and in this video we're going to be continuing our discussion on what we've left off with, right, our linear model, and we talked about loss functions and we talked about what our model is going to look like. We defined our model. Since it's linear, we're going to have our slope times our input plus our y-intercept, which is just our weight, our TU, which is just our temperature unknown, with unknown units, plus B, which is just the bias. And if this is confusing, that's because I'm talking about an example that we began in our previous couple of videos, in the past couple of videos, and that was a temperature conversion. For more context and for more information about this whole temperature conversion, example that we're going through, I would recommend going through our past few videos, because that will clear things up a bit. But just for your own information, right, we have a thermometer, we're getting temperature in unknown units. The output of our linear model is in Celsius, and we converted it to a tensor. And if you want more information on what it means to actually fit a model and what it means to, like, what this whole training and learning process means, I would definitely recommend checking out my past few videos, because it gives a lot of insight into what's actually going on. And it might seem as though I'm just jumping into stuff, but I'm actually not, and we did go over this in our previous videos. Okay, and so we have a linear model, and we need an initial set of parameters that will try to model our data. It's definitely going to be wrong because we are going to optimize it and we are going to change the parameters. Like I said in my previous video, if we have a line, right, we're just dealing with linear relationships right now. We're not going into that those nonlinear components, because we don't need to add to the complexity. It's already, like if we just take like 5 minutes or like 10 minutes or 20 minutes or whatever, and just sit down and go through what this whole process looks like, it'll be easier to add in those different components that make it complicated, or like more, yeah, it makes it more complicated. And so, for example, if we have a line, we can have different lines, but there's only one specific line that's gonna represent our data. And we need to try to find that line, because that line is basically the relationship between the input and the output. And once we have that, we can apply it on new data, just like we did it here. So for example, our actual data was probably 4x plus 9. We probably thought that it was x plus 2, which was completely wrong. But if we had a good approximation, maybe if we had 4x plus 8, that would be a good approximation. And if we just plugged in a new value, like 4, into our model, we would get accurate results. If we don't, then we're going to get ridiculous results that don't match at all. And it's going to have a high value for the loss function, which just means that, our loss function tells us how far off our predictions are from our output. So if we need to minimize that loss, and we need to minimize that loss function so that the actual values are the smallest that they can be. So our goal for this video is to figure out how we minimize that loss function. Okay, we talked about loss functions in my previous video, and what it means to change parameters, what that whole idea is all about. And also we're going to address it in detail in this video too. So if you don't have time, or if you don't, if you just want to go along with it, you can, but I think it would give you more information and more context before you jump right into this. Okay, so our goal for this video is to figure out, how do we change and update / estimate, right, W and B. How do we find the perfect slope and the perfect y-intercept that actually represents our line, right? Otherwise, we're going to have a completely different slope and a completely different y-intercept, and that relationship between our input and output is completely wrong. So we need to find the perfect slope and the perfect y-intercept, or in other words, the perfect parameters to best represent and model our data. Okay, so we need to estimate that so that our loss function, or like our loss, reaches a minimum. Okay, so how do we do that? Okay, so we will see. Okay, so in order to, minimize or optimize a function, okay, we're going to need to find the derivative, right? So, like at a specific point. So what do I mean by that? Well, hopefully you've brushed up on your calculus skills. I mean, it doesn't need to be like extremely advanced, right? You just need to know how to take the derivative, which just means like if you have, a curve. Okay, it doesn't really work that way with a linear relationship, but if you had like a curve, a function that's, that's not a straight line, the derivative of a straight line is just constant, right? A straight line is constant. So what do we need to, minimize our loss function with respect to, right? What do we, like with respect to what? Well, it's going to be with respect to our parameters. Okay, before we jump into the derivatives and, whatever, okay, let's take a look at what we're doing here. So we have initial values for our W and our B. So in order to, figure out whether it's right or not, whether this actually represents our data or not, whether this slope and this y-intercept, this weight and this bias actually represents our data, we need to go through this iterative process. So we first say, oh, W is 1, our slope is 1, and B is 0, okay, which is completely wrong, right? It's just an initialization of these two parameters. So, what we do is, you can think of it as, twisting a knob, or a number guessing game. So, for example, if we have a number like guessing game, and maybe you developed this yourself and wrote out a little code that does it, and maybe our secret number is like 12. Okay, maybe that's our secret number. And in order to relate this to our parameters optimization, or like, our loss function minimization sort of problem, we can think of this magic number or secret number as our parameter. So we need to figure out what that is. So we guess a number. Okay, so an initial guess is 1. Okay, and then 1 we figure out is too low. Okay, and then we go a little up. Okay, and then we guess maybe 5. Okay, too low. Okay, so it increased a lot. Okay, maybe let's increase it by the same amount. So 4, right? So let's do 9. Okay, too low. Okay, so how much is it increasing by? Increasing by 4, right? Okay, that's still too low. Maybe let's try something else. Let's increase it a little bit more. Maybe instead of, 13, let's pick 14. We get too high. Okay, maybe let's go somewhere in the middle, like, what's in the middle? 10, and then 13, and then 11, and then 12. Maybe like 11, I don't know. Okay, okay, too low. Okay, so it's in between 11 and 14. Okay, maybe 13. Too high. Okay, So 11 is too low, 13 is too high. I know it's 12. Okay. We get perfect. Okay, so that's the same iterative process. I mean, like, if you're familiar with loops, which you kind of have to, right, if you are going through this, PyTorch tutorial, you're going to need to know about, like, actually iterations are just, like the way we use it in real life, right? We iterate through, if we iterate through, this sort of guessing game, it's like trial and error, okay? We try things, it doesn't work out, we try another thing, in an educated way. We're not just doing this blindly, okay? We're not, just, being stupid when picking these values. When we say, oh, 5 is too low, we didn't pick 4, because that would also be too low, right? So we're being smart about how we're guessing, okay? That's what the model does. Your machine learning model, which is just, once again, let me reiterate, it's just this mathematical web. Right now, it's not a web, really. It's just linear relationship, y equals mx plus b. But, it's just math, okay? And so what we need to do is that we need to find the best slope and the best y-intercept that models our data. And 1 and 0, like the way we initialized it here, right? A tensor that just holds the scalar value 1, and the tensor that just holds the scalar value 0 for b, right? That's an initial value, and once again, it's not going to work out because it's just random, right? So we, just like how 1 was random, okay? And the model figures out based on, based on the actual answer, is this too low? Is this too high? Is this too low? Is this too high? Right? We're testing out different values for our W and B. Okay, let me put that in bold here. So just like this, we are testing out different values for our W and B. So let's dive a little deeper into, how our guessing game figured out that this was too high or too low. I mean, this is probably common sense to you, but if you put that into words, you'll see how we can do it with our model, or machine learning model. So we took a look at 1, okay, which was our prediction. We took a look at the actual value, okay, and we checked out the difference between the two, okay, and based on that difference, although this number guessing game isn't exactly the same as this W and B, right? It goes along the same lines as that, right? We are just trying to figure out the best value. So we're taking the difference, okay, between these two, between the predicted value and the actual value. Okay, so that's what we do with our situation too. So how are we being intelligent about what values we're guessing for our W and B? Well, we take a look at the loss function. Okay, because the loss function tells you, I think I wrote this above as well, but I'm going to be writing this down again here, is that it tells you, how far the predicted value is from the actual value. And what else does this tell you? Well, it tells you, if you put this in other words, right, it tells you how wrong you are. Okay, so this is what's going to tell you by how much or in what direction do you need to change W or B, right? By direction, I mean, like, do you need to go up or do you need to go down? For 1, if you picked 1 and you found out that it was too low, do you go up? Is the direction you go up, or is the direction you go down? Well, the direction you go is up, right? Because we figured out that it was too low. Same with what we're doing with our parameters here. Okay, we take a look at the loss function, right? Because the goal is to minimize the loss function. We want to be as close to, we want to represent the data as best as we can. So although we don't want to overfit, which we'll talk about later, which just means you're being really, like, too correct and you can't generalize. So that's what overfitting is. But, like, if you want to have at least an accurate representation of your data, then you're gonna need to minimize your loss function. Okay, so, and you need to know in which direction. Okay, which direction do you need to update the parameters? Do you need to go up? Meaning, do you need to, like, increase it or decrease it? And an important point that you should note is that if you twist too much, right? For 9, we twisted the knob too much, meaning we increased it by too much. And you can also think of it as a knob, right? Like, you want it to be at a certain point, but you slowly twist it and twist it and twist it, but you pass the point that you want to be at. So that's what I mean by twisting the knob too much. And this is what we mean by going too high, updating it too much. Okay? Because at this point it was too low, right? If we just went slow enough, if we just went maybe like 11 and then 12, we would have been at the right point. But we twisted the knob and we went up and updated the number too much so that we increased the loss again. If this were an even bigger number, maybe like 25 or something, and I know that's not realistic, that's not a realistic guess, but if we were to go a little higher, then our loss would have increased. We would have gone further away from our goal, if we do it too much. So we need to make sure that we're updating our parameters slowly, but not too slowly. Otherwise, it's going to take too long, right? If we just did 1, and then 2, and then 3, and then 4, and then 5, right? That takes too long, right? If there are tons of parameters and we're trying to do that like this way, it's going to take way too long. But also, if we update it too quickly, we're going to increase the loss. Okay, so there are two problems, and you want to, find that good balance there. Okay, and after a point, it does converge to a minimum loss. Okay, if you at this point, at this like ending point, although it's never going to be perfect, right? We do, in like a real world situation where we have a lot of parameters, not just our slope and our y-intercept, it's not going to be completely perfect, but even in this linear situation, it's not completely perfect because our line isn't, just a straight line. It's a fuzzy line like we talked about. So it's going to converge. So our loss, okay, actually, we do converge to a minimum loss. Okay, so after a certain point. Okay, and the algorithm that will allow us to do this with our linear relationship is called gradient descent. Okay, and if you are, if you're twisting your knob, okay, we've already noted the point that we can't do it blindly, and we can't, be stupid about it. We can't just twist it however much we want. There needs to be some sort of methodology. Okay, here we said, oh, let's increase it by the same amount. Okay, the methodology that we're going to use is pretty similar to that. So what we are going to do is we're going to compute the rate of change of the loss, like I said. Compute the change of the loss with respect to each parameter. Okay, and this is just the change of the loss. This is just the rate of change. Okay, this isn't the parameter, right? This is the rate of the change of the loss, right? How much are we being wrong with respect to the parameter? When I'm just focusing in on W, how much is my loss going wrong? Okay, so you know, this is also not just like when we're zeroing in on each parameter. This is also like in a calculus sense of like taking the derivative and computing the change. Okay, but let's start off slow. Okay, and we're gonna modify each parameter. Okay, this is the rate of the change of parameter. My question is, how do we update the parameter? How much do we add or subtract to it? And I'm telling you that we're going to be modifying each parameter. We're going to be updating it by a small delta x in the direction of the increasing loss. Okay, and you expected that. Okay, what's the new thing here that I'm saying? Of the decreasing loss. Okay, this is pretty straightforward, right? We want to go in the direction of the decreasing loss. Just like here, our loss is getting smaller. Like when you compare 1 and 12 and 5 and 12, the loss is definitely going down. And we want to move in that direction. So we're moving in the right direction. Okay, that's what that's saying. But you knew that, right? What is it like? How's that related to this? Okay, well, let's take a look at how we're going to be. Let's first take a look at how we're defining the rate of change. Okay, and then we can modify it based on this number. Okay, so based on the rate of change, okay, based on the rate of change, we are going to be modifying the parameter. Okay, and okay, but it's not exactly by the rate of change. We're going to do something to the rate of change and then modify it, but it's definitely dependent on the rate of change of the loss. Okay, so we do that. Let's first define our delta x, or just our delta, which just means change. Right, so that's our delta. And we define our loss, you know, rate of change of the loss. I'm going to call it loss rate of change. And we need to do this with respect to each parameter. Thank goodness in this situation we only have 2, right? When we have a lot, we're going to be dealing with that situation when it comes. We're not going to be defining a rate of change for each one, so you can look forward to that. But we only have 2, so let's go through that entire process, which is what this whole video is about. Which is what this whole series of videos are about, especially with when I'm using, you know, this Jupyter notebook. We're going through. I feel like in each one of my videos we use the same Jupyter notebook, so I think you can look for that. But you know, this whole process is just to give you an intuitive understanding of what is going on. We're not going to be doing this for each one, right? It's just like, you know, when you learn about limits. you first probably learned about taking this small delta x in your calculus class. And if you aren't familiar with calculus, I would just recommend going through a few introductory videos. And I also think I'm going to be making a calculus course soon, so you can look forward to that. But it would be good to familiarize yourself with these calculus skills, just basic ones like taking the derivative and maybe taking the integral. Actually, I don't think we're going to be needing the integral in this video, right? But it would be good. Okay, by the way, so let's go back to our the thing that we were working on. So let's take the rate of change of the loss with respect to our W. So let's make a comment because I know this variable name is kind of confusing. Rate of change of the loss with respect to W. Okay, and we're going to be doing that, and this just means I'm going to be defining this on the next line, because if I don't do that and if I define the variable on the next line, Python's going to get angry and scream. But let's say the loss function, which we've defined above, of our model, okay, tu, comma, w plus delta, tc, and let's take tu, b. I'll be going through this in just a second. Let me just type it down first, and then we'll get to it. This function model tu, comma, delta, w minus delta this time, comma, b, tc. That's strange. 1 second. Okay, where did this parentheses go wrong? Okay, loss function. So first we're just taking a look at this. So the loss function model tu, this w delta is not supposed to be like that. And like that. Okay, I think that's it. Okay, so what did we do here? I know this is probably confusing, or maybe not, but, so we have a loss function. Okay, we have a loss function. This is the rate of change of the loss. Okay, so you can expect to see some subtraction. Okay, change in y over change in x. And we have our delta. We have our w, which we're changing by delta. So that's going to be our change in x. And so, we're going up delta and we're going down delta. So we have like two, deltas that we got to deal with. And that's what we're dividing. So what we're doing here is, rate of change is just, y1 minus y2 over x1 minus x2, right? So the loss minus the loss, because that's, the y value of the loss function, and our x is going to be our delta. So that's what these are the parameters our model takes in, and this, like the predicted value and the actual value. Okay, so the model, this is going to be, like if I could highlight this, this is going to be our predicted value model, and then like we have in like whatever, that's going to be our predicted value, and TC is our actual value. Okay, so that's what's going on. And like I said, we need to change the parameters slowly because we never know when it's going to be too much. But we also want to be reasonable about it. So what we do is that, first of all, we have our rate of change, okay, which is basically the same thing I was considering when I was going up in my number guessing game, right? I was going up by 4, and then I went up by 4 again, but then I went up by, like, did I go up by 4 again? I went up by 5, I think, okay, and then it was too high and whatever. So just like we took a look at the difference between these two values, we're taking a look at the rate of change of the loss with respect to W. Actually, it's not similar at all to what we did. Actually, we should have looked at 12, and but this is just a regular guessing game, so it doesn't matter. But what we're doing here is we're updating the parameters based on how much the loss is increasing or decreasing, and we want to go in the direction of the decreasing loss. Okay, so as we update our parameters, how much is the loss decreasing? Okay, how much are we getting closer to our goal? That's what we want to know, and that's what we are figuring out here. And based on that, we can update our parameters. But like I said, we need to be diligent about it, and we need to, update our parameters slowly. So what we do is we scale the rate of change of the loss, and then we update the parameters. Okay, so what we do is we have this other hyperparameter. We call it a hyperparameter, which is something we can, play around with. And we'll talk more about that later. But, applying a change to W, that's, proportional to the rate of change is good. But like I said, we need to update it. So we're going to define a new sort of thing called a learning rate. And this is the value we scale that rate of change by. So let's say 1E2. It needs to be a smaller number, a really small number. So we have W. We're redefining W. We're redefining our weight as our original weight, which was initialized randomly. And we're going to subtract the learning rate. Okay, that's the value we're scaling. The loss of the rate of change of loss with respect to W. Okay, so that's what we're doing, and we need to scale it by a small number called the learning rate. And you can pick the learning rate. It can be whatever you want as long as it shows you the results that you want. Okay, so we run it. Okay, we didn't run the previous stuff yet, so W isn't going to be defined. But we're going to do the same thing for B. For our bias, let's just copy it. So instead of changing our W by delta, we're going to be changing our B by delta. So plus delta, and minus delta. Okay, and it's going to be the rate of change of loss with respect to b this time. So let's do that. Okay, we didn't run it. We didn't run the previous stuff yet, which we should. But, you know, let me just do this and we can run it soon. So b is equal to b minus the learning rate times the loss. Okay, so let's run it. And okay, actually, let's start from the beginning. Maybe it didn't run. Okay, here. Okay, this should be a markdown cell. Rate of change. Okay, this is... Okay, run it. Squared diff is not defined. Didn't we define our loss function up here? Squared diffs. 1 second. What am I do? Wait, what? Oh, in our loss function. Okay. So instead of diffs, I said diff. So we run it. So now, okay, now it's good. Good, good, and good. Okay, in our next video, we're going to be talking about how we actually use derivatives for this purpose. Okay, so now you get the understanding. It's, okay, I think I began talking about something, but then I didn't continue it for some reason. Okay, so what I was saying earlier is that, you know how in a calculus class when you, you first talk about limits, you first talk about, this whole crazy, like definition of instantaneous rate of change, or maybe it was average rate of change, and you use extremely small values, and then you're like, hey, there's an even better way to do this using limits. And then you move on, and then you talk about limits, and then you say, hey, there's an even better way to, compute these different limits at certain points, and we call those, like, specific limits derivatives, okay? And then, like, it's like that. So we start off with, like, hey, we're using a small delta, and then just like in a calculus class, we will move on to derivatives, okay? But this video's running a bit late already, so we'll save that for next time, and we will, see how derivatives actually play a role in the machine learning process. I know I described it as just being part of it, but in our next video, we'll actually see how. Okay, so thank you so much, and I hope you learned something new today in this video about how we change, update, and estimate W and B so that our loss reaches a minimum. We'll actually be continuing that discussion in our next video using real derivatives and vectors of derivatives, which we call gradients. Okay, but you don't need to worry about that now. I hope you learned something new today, and don't forget to like, comment, and subscribe.